Nuclear power plants are largely unknown entities. Beyond appearances on The Simpsons, few of us know about nuclear power plants, how they work, how they operate, and where they get their energy from. Well, today is the day. Today you will learn in depth how a nuclear power plant works. Are you ready? It all started in 1934 with Enrico Fermi. Fermi bombarded neutrons against a sample of uranium, aiming to obtain heavier elements. His results were confusing. Years later, Otto Hahn and Lise Meitner repeated the experiment. Barium seemed to be appearing in the sample, but this couldn't be. Barium has 36 fewer nucleons than uranium. Could it be that uranium was splitting in two? If so, upon splitting, it would release excess neutrons that could trigger the same reaction in other atoms and so on. A chain reaction would begin, a process with a tremendous release of energy. By 1942, Lise Meitner, of Jewish origin, was forced to flee Germany, taking with her the key to mass destruction. The world would never be the same again. A chilling story that soon led to the launch of the first nuclear bombs on Hiroshima and Nagasaki. After World War II and during the Cold War, a peaceful way to use all that energy contained in the nucleus emerged: nuclear power plants, which today provide energy and electricity to millions of homes around the world. To understand all this well, it is better to start from the beginning. An atom consists of a positively charged nucleus and electrons orbiting around it with a negative charge. Inside the nucleus, very interesting things happen. There are protons and neutrons with a curious cocktail of forces. The electromagnetic force tends to separate them, and the strong force tends to unite them. This cocktail of forces is good for the atom. In fact, the more elements there are, the better. Two protons with two neutrons in helium are more comfortable than forming two separate deuterium atoms. In physics, being more comfortable means having less energy. To account for this, we use a quantity known as nuclear energy. It is found that, as we add more protons and neutrons to the nucleus and move up the periodic table, the nuclei become more and more comfortable. That is, their energy per nucleus is lower. This is similar to what happens when you share an apartment. If you and your girlfriend live separately, you might each pay $600 for the apartment. When you move in together, you need a bigger place and might pay more, maybe $1,000, but it is less than the total sum. You save $200. If now you join another couple, the place will be bigger and you'll pay more for it, maybe $1,500, but less than if the four of you lived separately, which would cost a total of $2,400. Similarly, the energy per nucleus decreases as we move from hydrogen to helium to lithium to boron and so on. But nuclei, like houses, have a limit. There comes a point where instead of generating a saving, they generate an extra cost. This happens in nuclei starting from the atom with atomic number 26, that is, 26 protons and 26 electrons. We're talking about iron. Iron is the most efficient and therefore the most stable element in the universe. It has the lowest energy per nucleus and therefore where the nuclei are best compressed and most comfortable. In other words, all atoms want to be like iron. What happens beyond iron? There are still heavier elements whose nuclei are less comfortable. This can be seen in a famous curve showing the energy per nucleus for 240 elements of the periodic table, from hydrogen to uranium. Although the shape of the curve seems to indicate that the peak is at iron, we are talking about binding energies, which are negative energies. So what appears to be a maximum is actually a minimum. In this universe, where everything tends to be in a state of minimum energy, all atoms want to reach that state. The process by which small atoms unite to reach a lower energy state is called fusion. The breaking of atoms to seek stability is called fission. These are two mechanisms operating in the universe to achieve that desired stability and minimum energy. In fusion, we start with two small atoms that unite to form a larger one, releasing energy. In fission, a large atom splits into two smaller ones, also releasing energy. Fusion occurs, for example, in stars, where very small atoms like hydrogen fuse to generate, for example, helium, a process that produces energy which we see in the brightness of the sun. While fission is a process that occurs, for example, in nuclear reactors. In both cases, the energy released is enormous. While the binding energy of electrons, typical in chemical reactions, is on the order of electron volts, the binding energy of nuclei, typical of nuclear reactions, is millions of times greater. We're talking about mega electron volts. Although a mega electron volt might seem insignificant, a single atom releases that energy. Imagine that this process in one atom triggers a similar process in neighboring atoms, creating a chain reaction. In a piece of material weighing a few grams, there are on the order of 10 to the power of 23 particles. So that tiny energy in one atom, when expanded to millions of atoms, releases tremendous energy. We're talking about millions of joules. This is the power of atomic bombs and nuclear power plants. This is precisely what Otto Hahn and Lise Meitner observed, realizing the great power generation capacity of this process. They worked on fission, which is what happens in current nuclear power plants. To obtain energy from fission, two things are needed: fissionable material and a way to maintain a chain reaction. The fissionable material par excellence is uranium-235. Unlike other elements that disintegrate by alpha or beta emission, uranium-235 splits in two, releasing a large amount of energy. Fermi achieved this reaction by sending neutrons against uranium nuclei. Neutrons, having no electric charge, easily penetrate the nucleus, creating fission. This is very interesting. A material like uranium fissions when it receives neutrons. But the question is, how do we achieve a chain reaction? Lise Meitner had the key. The fission of uranium by the arrival of a neutron results in two smaller atoms, energy, and 3 neutrons. These new neutrons can fission other atoms, releasing more neutrons in an exponential escalation of energy. If this escalation is uncontrolled, we have a bomb. But if controlled, we have a nuclear power plant. Two details are missing. The first is that uranium-235, the fissionable material, is very rare. Its older brother, uranium-238, is much more common. In a piece of uranium ore, 99.3% is uranium-238, which is not fissionable. Therefore, natural uranium, which can be extracted from a mine, is not useful as raw material for a nuclear power plant. We need to enrich it, increase the proportion of uranium-235. Enrichment basically consists of increasing this proportion. For nuclear bombs, uranium enrichment leads to a concentration of more than 90% uranium-235. For energy applications, between 2 and 5%. This low enrichment ensures that it does not become a bomb. The second detail is that neutrons, when slower, have more ability to fission atoms. Therefore, it is essential to slow these neutrons down. For this, a moderator is used, which absorbs energy from the neutrons to slow them down. Moderators like water or graphite are useful for this. We now have the theoretical elements to understand how a nuclear power plant works and the extraction of energy from atomic nuclei. But how is it done in practice? Let's start with a question. How do we obtain electricity from uranium fission? For this, I will describe the operation of a pressurized water reactor, the most common in the world. Uranium is found in fuel elements inside the reactor vessel, which is like a huge pressure cooker where water circulates to function as a moderator and coolant, extracting the heat generated by the fissions. This is what we call the primary circuit. It is common for a nuclear power plant to have 2, 3, or even 4 circuits that extract the heat produced within the core. Each circuit has a steam generator, a heat exchanger with tubes. Water from the reactor, primary circuit, passes through the inside of the tubes and gives up some of its energy as it cools before returning to the reactor, driven by a coolant pump. The primary circuit is kept at high pressure, about 157 atmospheres. Let's return to the steam generator. The water from the primary circuit cools as it passes through the steam generator because outside the tubes there is lower temperature water from the secondary circuit. As the secondary circuit water enters the steam generator, it comes into contact with the hot tubes and turns into steam. The steam is transferred to turbines and drives them at high speed, approximately 1,500 revolutions per minute. The turbines are connected to an electric generator, alternator, which, when rotating, generates a large amount of electrical energy. This energy is transferred to transformers that increase the voltage suitable for transport to consumption sites through high voltage lines. What happened to the steam that moved the turbine? It lost energy and falls into a large tank called a condenser, where it condenses and becomes liquid water again. For this, it is necessary to have a cold sink, that is, something colder passing through the condenser, usually water from a river, lake, or the sea. Once we have water again in the secondary circuit, we preheat it and pump it towards the steam generator to complete another cycle of the secondary circuit. And that's it. That's all for now, folks. I hope you enjoyed this video very much. Study hard and stay curious. Maybe you will be the next Enrico Fermi.